next conic section, which is hyperbolas. So, one definition of a hyperbola is the following. A hyperbola is the set of points x comma y satisfying one of the following equations. So here is one equation for a hyperbola. X minus h quantity squared over a squared minus y minus k quantity squared over b squared is equal to 1. If you notice, this equation is exactly the same as the equation for the ellipse, except instead of a plus in between these two terms, you have a minus sign. That is one form of the hyperbola equation. However, what's interesting is that hyperbolas actually have a second equation, and I'll write that down here. It is exactly the same as the first equation, except the order of the terms is reversed. So in the second form, we have y minus k quantity squared over b squared minus x minus h quantity squared over a squared equals 1. Now, I'll explain the difference between these two forms in a moment, but let's just see what this thing looks like. So, a lot of similarities with ellipses. First of all, we have something called the center, and just like with ellipses, the center is given by the coordinates h, comma, k. So, there's the center located at h, comma, k. Then we have vertices. We have, they're given by a and b, just like before. So just like before with ellipses, the value of a tells you the distance between the center and the left-right vertices. So I have a vertex here, and this distance is a. And I have a vertex here, and that distance is also a. We also have, just as before, B gives you the location of, sort of like up-down vertices. So if you go B units up from the center and B units down from the center, you get these additional points here. And so far, this looks exactly the same as the setup for an ellipse. But rather than drawing a circle through these 4 vertex points, instead what you do is you draw a box like this. Now I'm making it in dashed lines because this box is not actually the graph of the equation. This box is not actually the hyperbola. Rather, it's just an aid in drawing the graph of the hyperbola. Similarly, what I'm going to do now is I'm going to draw 2 lines, the diagonals of this box, of this rectangle. And they're also going to be dashed because they are not part of the hyperbola, but again, just an aid in drawing the graph, in constructing this thing. So now that I've got this picture of a box with the diagonals drawn, I'm ready to construct the hyperbola. You see these 2 points right here. The hyperbola actually has 2 pieces. One piece looks like this. It sort of hugs the wall, comes through, goes through that vertex, continues to hug the wall, and goes out. And on the other side, the same thing happens. Hugs the wall, goes through that vertex, comes out, hugs the wall. And that's the graph of the hyperbola. A quick note, notice that if you're sort of really paying attention, you might have noticed that of these 4 points, 1, 2, 3, 4, I only called these 2 points vertices. Technically, these 2 points are not called vertices in the case of a hyperbola, which is a bit strange, but technically it's just the 2 points that the hyperbola actually goes through that are called vertices. I want to mention that just like ellipses, we have these things called foci. And exactly what the foci are and what they do is kind of a mystery that I think I might just postpone for right now. But let's just make it clear that there are these special points called foci. And in the case of the hyperbola, they're going to be here and here. And as usual, I designate foci using, using stars instead of dots. In the case of the ellipse, we had this extra value called c, which gave you the distance between the center and the foci. That is true here as well. We have this distance c, which determines the distance from the center. So the distance from here all the way to there, that is c. And once again, c is not a number which appears in the actual equation of the hyperbola. Rather, it is a number which is given by a formula. However, the formula for c when it comes to hyperbolas is different than it is for ellipses. For hyperbolas, it's c equals the square root of a squared plus b squared. If you remember with ellipses, it was very much like this, except there was a minus. And if you remember, actually, for ellipses, there were two different formulas for c. One was a squared minus b squared, and the other was b squared minus a squared. Fortunately, in this case, we just have one formula for c. It's a squared plus b squared. So just a couple of things to notice about this. In this diagram, you'll notice that these diagonals, the diagonals of the rectangle that I drew, these diagonals form kind of an invisible wall that the graph of the hyperbola runs up against. These diagonals are actually asymptotes. And what that means is that if you follow the graph of the hyperbola way out, and it does, of course, continue, that's the meaning of these arrows here. If you follow the graph way out, the graph gradually gets closer and closer and closer to the asymptote, just gets closer and closer and closer. One of the kinds of things I'll have you do in the problems is I'll ask you to find the equations of these asymptotes. Okay, so now, of course, I mentioned that there is a second formula for hyperbolas, this one here. It's the same exact formula, except the terms are reversed. So what's the difference between these two forms? Does the graph look different for this one? Yeah, the graph does look different. If you notice in this picture, I drew two pieces of the hyperbola, one to the left and one to the right. In this form of the equation, the picture is identical in every single way, except the two pieces of the hyperbola will be above and below. So let's just run through that again. It's worth seeing twice how this thing is constructed. So if I want to graph this hyperbola, what you do is you start by plotting the center, which is located at h, k, as always. Then we plot the sort of 4 points, up, down, left, and right, using a and b. A still gives you the distance between the left-right points, so that's still a, and this distance here is also a. And b still gives you the distance, up and down, so we have these 2 points here, this distance right here, that's b. And just as before, I'm going to now use these 4 points to construct a rectangle, a box. And then I'm going to draw the diagonals of this box. And those diagonals will actually be the asymptotes of the hyperbola. Okay, there are my diagonals. Now, I want to re-emphasize a point that I made last time. Even though I've drawn these 4 points, up, down, left, and right, technically only 2 of them are considered vertices in the case of hyperbolas. In this formula, the first formula, the points to the left and the right of the center were called vertices, and the graph went through those 2 points. These 2 points, the points above and below the center, just don't have names. A little bit strange, but they just don't have names. Here the situation is reversed. This point here is a vertex, and this point here is a vertex, the points above and below. The hyperbola will go through those points, and these 2 points here just don't have names. The ones to the left and the right just don't have names in this version. So let's draw the actual hyperbola. Of course, the graph is sort of, approaching that vertical wall. It's hugging the wall. It goes through that vertex. It comes through. It approaches the wall. That's one piece. And then the other piece is the same thing, but down below. So it's hugging the wall, goes through that vertex, hugging the wall, and that's basically it. One key difference that I have to point out is that here in the first picture, the foci are to the left and the right of the center. Here, they will be above and below the center. So the focus, one focus should be around here, and another focus should be maybe right down there. And just as before, C, which is still given by this very same formula, okay, C is still given by root a squared plus b squared. That C is the distance, once again, between the center, right here, and one of the foci. So at the risk of making my picture too cluttered, maybe I'll use a different pen. This distance right here, that is C, distance between the center and one of the foci. Okay, I suppose I should tell you sort of what the foci mean geometrically in this problem. Maybe just a quick recap of what the foci meant in the context of ellipses, which I explained in class, but I don't think I explained in the video. I just referred to it. So let's go back to ellipses for just a second. And let's suppose that you have a piece of string like this. It's actually an elastic, but I'm going to pretend that it is a piece of string that cannot be stretched. And let's suppose that you nail the two ends of the string at some points. So maybe right here and right here. And what you do is you just, nail the ends of the string at those points. So the ends of the string are fixed right there. Now what you do is you imagine, so hold those points fixed, okay, and now pull the string taut, okay, and just allow yourself to kind of sketch while keeping the string taut, just kind of go like this. Hopefully what you can see is the bottom half of an ellipse. I'll now draw the top half as well. So how is it done? Well, you keep these points fixed, and then we pull the string taut, and we just sort of go around like this. There we are. Pretty sloppy, but you get the picture. Those points, as you've probably guessed from the fact that I've used stars to represent them, are the foci. So one interpretation of the meaning of the foci in the context of an ellipse is if you attach a string, the ends of the string at these points of a certain length, and you do what I just did, you will get the ellipse. Another way of sort of interpreting the meaning of these foci, the meaning of these points geometrically, is the following. Pick any point on the ellipse, say this point right here, okay? Look at the distance from the point you chose to one focus. That's the length of this line right here. And look at the distance between the point you chose and the other focus. That's the length of this line right here. The point is that the sum of these two distances is always the same no matter which point on the ellipse you've picked. For example, if I pick a new point over here, okay, and I'll use dotted lines this time to distinguish it from the first lines. If you pick this point right here and look at the distance from this point to the first focus, and look at the distance from this point to the second focus, if you add those two lengths together, it'll be the same as what you got the first time. That is, the sum of the lengths of the two dotted lines is the same as the sum of the lengths of the two solid lines, which of course makes sense with the string, because if you look, what you're getting here, the total length of the string is fixed, right? So whether I put it here or over here, right, those two lengths are going to be constant because the length of the string is fixed. And the sum of those two lengths is the length of the string. Now, back to hyperbolas. I think it's useful to review ellipses from the perspective of foci first, because the description of hyperbolas in terms of the foci is similar. So, so what is the sort of geometric understanding of a hyperbola in terms of the foci? Well, suppose that you've got some hyperbola. Okay, maybe it's a left-right hyperbola. It looks like this. I won't draw the whole box and everything else. Maybe it just looks something like this. Okay. And the foci are perhaps here and here. So now if you pick any point on the hyperbola, say this point right here, once again, look at the distance from this point to one focus. That would be the length of this line right here. And look at the length of this point to the other focus. And now consider not the sum of these two distances, but their difference, like this distance minus that distance. That difference between the two distances is preserved, no matter which point you pick on the hyperbola. So for example, if I pick some other point down here, once again, consider this distance from one focus, and then consider the distance from this point to the other focus. This length minus this length will be the same as this length minus that length, if I've drawn it correctly, which of course it's not to scale and it's very sloppy, so, but in a perfect hyperbola, that's true. So that's the relationship between, ellipses and hyperbolas. Okay, let's do a couple of examples. By the way, the geometric understanding of the foci, I want you to know that the foci have some kind of geometric interpretation, but for the most part, we're not really going to utilize the geometric interpretation in the context of the foci. So you don't have to worry too much about it. Okay, let's have a look at a specific example. Let's suppose that we want to, suppose that we want to graph the following equation: x minus 3 squared over 4 minus y plus 1 quantity squared over 25 is equal to 1. So first of all, you should recognize that this is a hyperbola, not an ellipse, because of the fact that there's a minus sign in between the two terms. So it's going to be a hyperbola. How do we graph it? Just like with an ellipse, you start off by writing down the center. So let's write down the center. I'm not going to sketch a whole grid. It's sort of just, or maybe I should. Hold on. Why not? Let's get some graph paper and maybe do it properly. I'll even use a pencil, which I sort of usually hate doing. So I'll make the grid in pen. Beep, 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 beep. And like this. That should be plenty of space. So let's see what this thing looks like. All right, so I'm going to start with the center, which is located at h comma k. H is 3, k is negative 1. So 3, negative 1, and that is the location of the center. Now I make the 4 points above, below, left, and right, just like I did with an ellipse. This is a squared, so a squared is 4, meaning a is 2. So if I go 2 left from the center and 2 right from the center, I have those 2 points. Similarly with b, I notice that b squared is 25, so b must be 5. Start at the center, go up by 5, 1, 2, 3, 4, 5, and down by 5, 1, 2, 3, 4, 5. And now, if this were an ellipse, I would basically be done. I would just, draw the ellipse. But remember, it's a hyperbola. So what do I do with these 4 points? I make this box, right? I make this rectangle, like so. So here's my rectangle. And then what I do is I draw the diagonals of the rectangle. I might even get a ruler to do this properly. If I can find one. No. I guess I can't find a ruler. That's strange that I can't find a ruler inside of a classroom. Seems like a thing that you would have. Anyway, I do have a stapler, which is straight. So I'm going to use this as a straight edge. I'm going to make my diagonals. Here's one. And then here's the other. Here we go. That looks pretty reasonable. Okay, so I've got my 2 diagonals. Those are the asymptotes of the hyperbola. Now I guess you just sort of have to decide, is this thing supposed to be a left-right hyperbola, or should it be an up-down hyperbola? If you look at the form of the equation, it's of the form x stuff squared minus y stuff squared. That was the first form. that I explained, and that's the form, that's a left-right hyperbola. So yeah, if the x term comes first, then, you know, it's a left-right hyperbola. So, all right, so the graph is going to look something like this. Graph is going to hug the wall, more or less, come down, hit that point there, which is a vertex, and then come back down. And then same thing over here. So it's going to kind of hug the wall. It's going to go through that other vertex right there, and voila. Okay, so those two curves are the actual hyperbola. All right, but there's more that we can do with this thing besides graph it. I would also like to find the foci. Now I know that the foci, because this is a left-right hyperbola, the foci are going to be to the left and the right of the center. The hyperbola always kind of hugs the foci, if that makes sense. So there's going to be one somewhere around here and one somewhere around here. To find the location of the foci, we need to know c, right? C is the distance from the center to the foci. So what is c? C is given by root a squared plus b squared, which in this case that would be root a squared is 4 plus b squared is 25. So that's root 29. That's obviously not a rational number. You know, just ask your calculator, what is that? It's going to be a little bit more than 5. Let me see if I can get a nice decimal approximation. It's like 5.38. So a little bit more than 5 is what we'll say. So that's the distance from the center to the left-right foci. So if I start at the center and go 5.3 units to the left, so 1, 2, 3, 4, 5, and then a little bit more. One focus right there. And now I'll start at the center and go 1, 2, 3, 4, 5, and a little bit more. There's my other focus. Okay? If you want to write down the coordinates of those points, they would technically be what? Well, the coordinates of the center were, of course, 3, negative 1. So the coordinates of this point will be, so it's root 29 units to the right of 3. So 3 plus root 29. The y-coordinate is the same as the center, so it's still negative 1. And then this focus over here would be 3 minus root 29, negative 1. Okay, so those are the exact coordinates of the foci. And there's just one more thing I want to do with this example. I would like to find the equations of the asymptotes. That's the diagonal lines, right? So I want to find the equations of the diagonal lines. This is pretty easy. Once you've got a picture. I mean, remember, if you want to find the equation of a line, several ways of doing it. You could do point-slope form. You could do y-intercept form. We've got lots of information on these lines. I'm noticing that, you know, so let's look at this asymptote here first. Let's start with that one. Of course, it goes through the point 3, negative 1, right? The asymptote goes through the center, and we can actually figure out its slope. You can see from here to here, it goes over 2 and up 5, right? So that's a slope of 5 over 2. So using point slope form, you know, y minus y1 equals m times x minus x1, we would have y minus y1. y1 is negative 1, so that's minus negative 1, which gives you plus 1, equals m, that's the slope, which is 5 halves, times x minus x1, which is 3, and that's the equation of that asymptote. The other asymptote, the equation can be found in a very similar way. You would just use this point and this point. I'll let you do that. I don't think you need to see me do that twice. So one more example before we wrap this up. I want to do one of these tricky examples where we just give you some random information about a hyperbola and you are asked to find its equation. So here's the setup. Suppose that we want to find the equation of a hyperbola whose center is at, say, 4, negative 2, has a focus at 7, negative 2, and a vertex at 6, negative 2. So we've just been given this sort of assortment of information, and we want to find the equation. With all these problem types, you should always just start by sketching a picture, right, of what you know. It doesn't have to be to scale, but so here's the center, and that's at 4, -2. What else do we have? We have a focus at 7, -2. Comparing the coordinates of these two, you see the y coordinates are the same. This point is just going to be a little bit, to the right, okay, of the center. So I'll use a star for that because it's a focus. That is. Okay, so what can we get from this? First of all, so you should first of all decide which form is your hyperbola going to be in. Remember, we have two equations, right? This one where the x term comes first, and then the second one where the y term comes first. Which one is our hyperbola going to satisfy? Well, because in our hyperbola, the focus is to the right, one of the foci is to the right of the center, we know that it looks like this, which means that the equation is of that form. So that's our prototype, right? So our prototype for the formula for the equation is x minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1. Now, we know that the center is at 4, -2, and that is the location, well, sorry, that's h comma k. As always, h and k give you the coordinates of the center, so we know h is 4, and we know k is -2. What else can we figure out from this? Well, this distance right here from the center to a vertex on the right, that has to be a. And of course, that distance from, going from 4 to 6, a must be 2. What else do we know? We know the distance from the center to this focus, which gives you c. c apparently is 3 from 4 to 7. Now, if you're looking at this equation, we have everything we need except for b. We have h, k, a, and c. How can we find b? Once again, you use the formula for c, which relates a, b, and c. So for hyperbolas, the equation for c is root a squared plus b squared. We just plug in what we know. We know that c is 3. We know that a is 2, so a squared is going to be 4 plus b squared. Now we just have to solve this equation for b. So square both sides, you get 9 is equal to 4 plus b squared. Subtract 4, you have 5 is equal to b squared. So we find that b is root 5. So plugging everything that we know into this equation will give us x minus h, that was 4 quantity squared, over a squared, which is also 4, minus y minus k. K is -2, so that's going to be y plus 2 quantity squared, over b squared, which is 5, is equal to 1. And that's the equation.